Hello, this is our Intergalactic space set.
Hello, I'm Fraser. I decided to design a satellite because it is mostly constructed out of simple shapes that has several different parts that are utilized for maximum surface area or volume. The satellite dish is maximized for surface area to send and receive radio transmissions. This required many calculations for hemispheres as well as one cylinder. As the surface area to volume ratio shows, I was successful in designing the satellite dish for surface area. This cube is designed for volume to contain satellite technology. This was the easiest part to calculate because cubes are very straightforward. I did, however, have to subtract the area of the back of the satellite dish that was touching the cube to get an accurate calculation for surface area. As the ratio shows, this was correctly designed for maximum volume. The solar panels are designed for surface area to intake as much sunlight as possible. For one part of these calculations, I had to learn how to calculate surface area and volume of a trapezoid, which was fairly easy once I figured out how the formula worked. The ratio shows that this was correctly designed for surface area. The total surface area added up to 15,968 millimeters squared, and the total volume added up to 21,555 millimeters cubed. The final ratio shows that overall the satellite has more volume than surface area.
Hi, I'm Teva, and I decided to design an international space station. My goal was to create a space station based on the ISS that had maximum surface area. Here, you can see that in some parts of my design it was made to intake as much sunlight as possible, thus needing maximum surface area, while other parts needed maximum volume to contain astronauts and equipment. Here are some of my calculations for my design. As you can see, this mainly focuses on the portion of my design that is made for maximum volume. Each shape required a different formula to calculate the surface area and volume. Here are more of my calculations for my design. You can see here that the majority of my design is created with 2D shapes. The solar panels, although 2D, end up having the most surface area out of all of the shapes in my design. They ended up contributing a lot to the total surface area. Overall, my total volume ended up being 1,348.3 millimeters cubed, and my total surface area was 5,581.28 millimeters squared. I had a total of 11 3D shapes and 49 2D shapes in my design. The overall surface area to volume ratio came in at 4.14 millimeters squared in surface area to 1 millimeters cubed in volume, which means that I did end up reaching my goal of creating a space station with maximum surface area.
I've created a 3D model of an escape pod for maximum volume. I've used many different formulas to calculate the surface area and volume of the 3D shapes within this escape pod. These 4 cones are used as thrusters to boost the escape pod, and they have empty space within them that is subtracted from their overall total. Cylinders are used as support thrusters with empty space within them that is subtracted from the overall volume, just like the cones. These hemispheres are used as a foundation for the escape pod. This big cylinder is meant to hold lots of individuals, which meant empty space was present and it needed to be subtracted. This ring is basically just an outline that helps support the structure. This hemisphere is the same as the other one. This cylinder is the top part with a hole. All of the totals were added to get a final total of surface area, which was 2,051 millimeters squared, and the total volume, which was 15,591 millimeters cubed, which leaves the ratio at 1 millimeter squared to 7.6 millimeters cubed. My prediction was correct, and this escape pod was meant for maximum volume.